Right, let's get started. So I've dragged you online on video through a fairly boring disquisition about all those relaxation rates and what they do and how. And now we will consider the interesting and practically useful part, and that is distance measurement, where all those relaxation rates play a role. So you've seen in the previous lectures that the two principal mechanisms by which spins relax in liquid state nuclear magnetic resonance is chemical shift anisotropy, from simply the fact that the molecule tumbles in solution, and that creates an oscillating term in the Hamiltonian, essentially noise. Noise has components at transition frequencies, transitions happen. And the second mechanism was dipole-dipole interaction between nearby spins, and once again, because the interaction is orientation dependent, what you have is noise in the Hamiltonian and therefore relaxation. Now, an important thing about dipole-dipole mechanism is it doesn't just drain the magnetization from a particular spin, it also moves it between spins. And so the topic of today's lecture is the associated effect called nuclear Overhauser effect. After Albert Overhauser effect, and the first picture we will consider is the energy level picture. And then we'll go into the time domain as soon as we understand it within the energy level picture. Right, consider a system of two spins. We have spin L and spin S, such that gamma L is bigger than gamma S. For example, protons and carbons, or electrons and protons, or protons and nitrogens, and so on. And I would remind you that the energy of a spin is minus mu dot B, where that's the magnetic moment and that's the applied magnetic field. So if the magnetogyric ratio is positive, like it is for protons, then the situation when the spin is collinear with the applied magnetic field is the low energy situation. We have a two-spin system. I assume that both of these are positive, and so the two spins being collinear to the applied magnetic field is in this case the lowest energy situation. Then if they are antilinear to the magnetic field, that is the highest energy situation, and our first spin has a greater magnetogyric ratio, so flipping our first spin, let's say from beta to alpha, should have a greater energy change than flipping the other one. So this is alpha beta, and that is going to be beta alpha. Right, so this is the flip of the second spin, this and that, and this transition is the flip of the first spin. Let us look carefully at the transitions that we have in this two-spin system. So we will have the flip of the first spin here and here. I'll denote that in yellow. And these are transitions that are allowed under the transverse magnetic field operators, for example Lx, and they're also allowed through the relaxation mechanisms, and I will put here the relaxation rate. So it's a single spin flip, or rather the projection change by 1, so I will put a 1 here, and this is the flip of our spin L, so I will call it WL1. So likewise here, 1L. For the S spin, smaller energy gaps, but also relaxation and coherent transitions can exist across these. So we are going to have likewise W1, but S. There are, however, also transitions here that are not allowed under our usual transverse magnetic fields that we use for manipulating spins. is a double flip here from alpha alpha direct to beta beta. So this is W2, and in the jargon it's called the double quantum transition, W2. And there's also a transition between the beta alpha and the alpha beta, that. And there is no total change in the spin projection, so this is called W0, the zero quantum transition. What is special about dipole relaxation mechanism is not only does it allow the blue and the yellow transitions here to occur, it also turns on the W0 and W2. So extra relaxation processes kick in that either flip two spins simultaneously that way or this way. Let us now think about what this is going to mean. And the spoiler, of course, is dipole-dipole interaction is distance dependent. And so whatever effect this is going to have will likewise be distance dependent. And that is the foundation of structure determination in magnetic resonance, in particular difficult cases where it's not essentially impossible by other mechanisms such as infrared. For example, it would be exceedingly hard to distinguish two diastereomers by infrared spectroscopy, but in magnetic resonance that would simply mean different distances, and if we find something here that's nicely distance dependent, well, we can try and do that. Okay, let us look at these rates. I will not derive those rates, I will simply give you the expressions for them. Unfortunately, relaxation theory is far too complicated for the full derivations to be given here, but let's just take a look and discuss. So W1 for spin L, a random coefficient that comes out of the algebra, but then meaningful things. Gamma L squared, gamma S squared, h bar squared to balance the units, and then r to the 6, and then tau c over 1 plus omega squared L tau c squared. A lot to take in, but let's take a look at the components here. Remember that relaxation rates depended quadratically on the amplitudes of the interactions responsible. We derived that in the relaxation theory lecture. You can clearly see here those squares. All right, so you've got the gamma squared, h bar squared, and of course asymptotically magnetic dipole interaction depends cubically on the distance, and so you have here r to the 6. So this is our amplitude squared term, which I have discussed when I was deriving the relaxation theory in general. And this is the spectral power density, so this is how loud the noise is at particular transition frequencies. This is the rotational correlation time, typically in the picoseconds and nanoseconds, and this is our Larmor frequency, so typically around a gigahertz for protons. So nothing unpredictable here. Expression for the Ws is very similar, except you just have omega s here. And let us take a look at W0 and W2. In this case, the noise will have to have the amplitude at the frequency that flips both spins simultaneously, in this case and in that case too. So we have, for example, for W0, again, just some numerical coefficient here, exactly the same pile of terms as we have had there, except now there's a tau c here, and then 1 plus omega L minus omega S squared tau c squared. So we will have to have the noise hitting the difference in frequencies between the two spins in order to activate this alpha beta to beta alpha transition. Right, so the first spin contributes omega L, but the second spin goes backward with omega S, and so this is omega L minus omega S. Then for W2, likewise, different numerical coefficients, 3 over 5, same pile of fundamental constants, but predictably we have the sum of the frequencies in the denominator. So omega L plus omega S squared tau c squared. Okay, so far so obscure. What would that physically mean in terms of quantities we can actually detect? Well, let us look at what our observables would be in this situation. So consider, for example, the LZ. Well, it will depend on the populations of all four levels. For example, if the populations are equal, then the spin is equally likely to be up and down. The expectation value of LZ will be 0. And if there's some imbalance in populations here, then it will be non-zero. And it's a spin half, so we get a half in front. And then let's think about it. So we want LZ. So this is our first spin. So we would want the population imbalance between alpha alpha and beta alpha, where the configurations are different. So this will be P beta alpha minus P alpha alpha. And likewise, we want the population imbalance across this transition. So we would have, in this case, alpha alpha, beta alpha, and then plus P beta beta minus P alpha beta. Right, so population imbalance across this, population imbalance across that, times a half, which is the spin quantum number here, and this is our expectation value for LZ. Likewise for SZ. So SZ, you have it in your handout, a similar collection of pluses and minuses on the populations. And these are the things we can actually detect. So in order to watch our distances, we should watch the longitudinal magnetization. And this, of course, we know how to do. We simply give a 90 degrees pulse and we detect it. Well, let us think about what is happening to these populations if we perturb some populations within this diagram. Well, firstly, there is, of course, the thermal equilibrium, right? The Boltzmann equilibrium populations there. If we just number those levels by the n, right? So the probability of the quantum system being in the energy level n is 1 over the partition function E minus the energy n over kT, and the partition function is just the sum over all such exponentials. So sum over n, e to the minus en over kT. Right? We know this Boltzmann equilibrium. Small deviations from equilibrium for probabilities follow essentially the same rules as chemical kinetics. So if we do have transitions between the energy levels, then the probabilities to first order for small deviations essentially flow around like concentrations. So if we know these rates and if we know those populations, then we simply have a kinetic network that pushes the populations around. And the full system of equations for n energy levels would be dp n's energy level by dt. We will have the sum total of all outflows in the same way as if it were a chemical. So we would have minus then the sum of all outflows, so omega n kn, right, times the current difference from the thermal equilibrium, so Pn minus Pn equilibrium, and of course the totality of all the inflows from all the other energy levels in there, and that would be plus, because it flows in, a sum over k, right, unequal to n over all the other energy levels, and then we would have omega n k, so the inflow and then the difference from the thermal equilibrium at that energy level. So this is essentially chemical kinetics, except we are looking not at variations from zero like we did in the ordinary chemical kinetics, but variations from the thermodynamic equilibrium. These are called Solomon equations. You will see them everywhere in quantum mechanics because they essentially govern the transport of probability across the quantum system, well, in some approximation. If we now apply this to our equations of motion, and I will not bore you with the arithmetic here, I will simply write the final result and then discuss it. We are going to have the following equations of motion. So d Lz by dt, so this is the longitudinal magnetization that we can actually detect, will be, well, as you know, we have the relaxation term, which would dump that population back to thermal equilibrium with some rate, and I will call that rate rho L for spin L, and this is just Lz minus Lz equilibrium. So that is the damping term that returns the magnetization to where it's supposed to be at the thermodynamic equilibrium. But the fact that we have W0 and W2 active here means that the spins talk to each other, and so a perturbation in the populations of one spin creates a perturbation in the populations of the other, and so there is an extra crosstalk term between them called sigma, a cross-relaxation rate, and then there's a deviation here between the SZ and the SZ equilibrium. So what essentially this means, that if we perturb the spin S from the equilibrium, we will see some perturbation also on the spin L, and that perturbation will be distance dependent, and so we have a hope of measuring distances that way. Then likewise for the spin S, d by dt is then minus rho S, the self-relaxation rate of spin S, Sz minus Sz equilibrium, and then plus the cross-relaxation rate with the L, Lz minus Lz equilibrium. So these are once again Solomon equations, but specifically for interesting observables of our specific two-spin system. So far, just common chemical kinetics, really, right? You can see that Lz is pushed towards the thermodynamic equilibrium by the self-relaxation rate and somehow perturbed by the cross-relaxation rate, depending on what is happening to the other spin. So the dynamics, the time dynamics of that, wait a few minutes. Let us first consider a situation that is quite simple. We would want, for example, to destroy all magnetization of the L spin. Just blast it with radio waves until the populations completely equalize between this and this pair of levels, and so we would have the Lz expectation value equal to 0. Right, so try Lz equal to 0, and secondly, we will do it for long enough, in practice, you know, maybe up to a minute in certain spin systems, that a new steady state has established itself. Steady state means the derivatives are 0. And so let us just plug everything in. Firstly, we will put this Lz to 0, and secondly, because it's the steady state, we will put the derivative to 0. So what this means is 0 equals minus rho S, then Sz minus Sz equilibrium, and then plus, that is 0, that is non-zero, it's just the equilibrium value. This becomes a minus, so we put a minus here, minus, and then sigma Lz equilibrium. Here, Sz equilibrium and Lz equilibrium are constants. They're given to us. They're functions of temperatures and energies and magnets and everything. But the Sz is something we would like to find, and let's see what it is equal to. So solving that for Sz. we would have to push that over to the other side. So we would have then rho s and then sz minus sz equilibrium equals sigma, and then here we have Lz equilibrium. Okay, opening these brackets and dividing by rho s, we are going to have Sz equals Sz equilibrium plus sigma over rho s and then Lz equilibrium. The magnetization of the S spin has been enhanced relative to its thermodynamic equilibrium value. Now imagine a situation where S is nitrogen and L is proton. The equilibrium magnetization on the nitrogen is small, right? Factor of 10 smaller than that on the protons. Assuming this is favorable, this coefficient, we can actually pump quite a lot of it up. In practice, you can get about a factor of 5 if you're lucky and the relaxation properties permit. Of course, these two have to be in the correct ratio, so let us take a look at the ratio here. So in sigma over rho s, at the steady state, I've got the lengthy expressions for you in your handout, but under the following assumptions. So if we assume a non-viscous liquid and a small molecule, so omega s squared tau c squared. Tau c is sufficiently small for this to be much less than 1. What this is going to asymptotically lead to is 1/2. After you plug in all the mathematics and the dust has settled. So turns out you can borrow up to half of the magnetization that the partner spin has by just saturating it and waiting long enough. It's rarely a half in practice because self-relaxation is usually faster than cross-relaxation, particularly if other mechanisms like CSA are present. They would make this self-relaxation rate even faster. But you can pump significant amounts of magnetization. And this is one of the uses of the Overhauser effect in magnetic resonance, improving the sensitivity. In a lot of cases, if you are doing carbon-13 spectroscopy, it actually pays to blast the protons for a few seconds before the experiment begins, particularly since you're going to be decoupling them anyway, so you're blasting them whatever. So to blast them for a few seconds for the Overhauser effect to accumulate on carbon, that can improve the sensitivity by a factor of 4. And of course, the time that the instrument takes to do signal averaging, right, to get you a factor of 4 is that amount squared. So you would save a factor of 10 to 16 in the instrument time by just doing it. So it is quite useful, and even more useful on the nitrogen 15. But our task here is not to just use it for signal enhancement, but to use it for distance determination. So I will also only mention one extra use case. It is when L is an electron. Now, electron is 653, I think, times more magnetic than the proton, and so you can actually pump giant amounts of magnetization from electrons to protons. That's called hyperpolarization, and that's a whole separate story. But there you need microwave electronics because, of course, electron frequencies are much higher than the nuclear frequencies in a given magnet. Okay, but for our purposes, we want distances out of that. So the second item on the agenda is the time domain picture. Let us go back to to these differential equations of motion and consider what is going to happen if we, for example, invert the first spin at the beginning of the experiment and we wait for it to recover. So let's say these are our expectation values, and that is time. And I should make that go into the negative as well, because we are going to invert our spins. So this is SZ for the yellow, and it will be LZ for the blue. Our L is the nucleus with the bigger magnetogyric ratio, so this is typically going to be the source of our magnetization. Its equilibrium value will be here somewhere, so LZ equilibrium, and we would want to invert it. So we do a 180-degree pulse. So if this is our L and that is our S, we start with a pi pulse in any phase, it doesn't matter, it's an inversion pulse on L. What then happens is we end up here in the negative expectation value. And what the relaxation is going to do for us is slowly return this to the thermodynamic equilibrium. So that is the equilibrium value. This is our initial condition, and so what is going to happen is it will exponentially recover to the thermodynamic equilibrium. But what is happening at the same time, look there. dSz by dt, well, S is sitting at its small thermodynamic equilibrium value here. So this is SZ equilibrium. Smaller total amount of magnetization than what we have on L. And it's sitting there and it's not doing much. And if S starts from the thermodynamic equilibrium, then this term S initial minus S equilibrium is 0, right? Because the initial is equal to the equilibrium. And so we only have this cross-relaxation term, and of course we have just destroyed the inverted, the L spin, so this is actually minus 2 times LZ equilibrium. Sigma is negative in non-viscous liquids, so this is a big positive source term on the S magnetization. So what is going to happen here is it will overshoot its natural thermodynamic equilibrium and its sensitivity would improve. And then, of course, as the perturbation on the L spin vanishes, this is going to drop back to its thermodynamic equilibrium value and approach it asymptotically. So what we are seeing is if we are pushing down the first spin, the second spin pops up by an amount that is a significant improvement on the thermodynamic equilibrium value. So in the sketch that I have made here, more than a factor of 2. And that's well worth fishing for. Now, if we make it a time domain experiment now, what can we do? Well, let's just wait for this time t. And this is called mixing time, Tm, because, well, the two magnetizations are mixing. And so we wait here for a time Tm, and at the end of that time, we do a 90-degree pulse on the spin S, pi by 2, and we detect spin S. So we record the free induction decay, we do the Fourier transform, and all the usual things. Then what is going to happen here if we make this experiment repeated? So we give it a small Tm, run the experiment, and wait for everything to relax. Run the experiment again with a different Tm. We will actually be able to sample the S curve. point by point. Right, so this will be our yellow FID. If we instead do a different experiment, simply just inversion recovery on the spin L, so pi by 2, that's literally an inversion recovery experiment, we will record the dynamics of the L spin. From this, we can fit those differential equations. So we can extract rho L, rho S, and sigma. So we have three things that we have extracted from there. And let's think about how many unknowns we have in that system. Well, we have the rotational correlation time, which is typically pretty hard to predict. You can do it with molecular dynamics, but it's a bit of a pain. So we can consider it a fittable unknown. And we have the distance. So we have three measured quantities. But, of course, there will be other contributions to rho L and rho S from the chemical shift anisotropy, so there are other unknowns in there. If there are too many unknowns, we can repeat these experiments at different magnetic fields, right? And then we get more variables, but we can essentially extract sigma, and sigma is what we want, and then out of sigma we get R, right? Distance. If that sounds laborious, wait for the next lecture when we will do the two-dimensional version of that, which measures distances all at once between all spins present in just one experiment. This is 1970s, I would say, where people would be recording a one-dimensional NMR spectrum, then setting the saturation transmitter at every spin in turn and watching what happens to the other spins, and if something happens, then they're nearby. And the extent to which it happens gets you, after a bit of mathematics, the interspin distance. Okay, so let us go through a couple of examples here. I've got some magnetization curves for you in the handout, but I would also want to consider a practical example. So if we have the spectral intensity as a function of frequency, what we would normally do is we would saturate the spin. So you would have, let's say, the original spectrum here with one signal, another signal, and some third signal. And let's say this is near, this is far, and this is saturated. So we picked one particular signal and we destroyed it. That other spin is far from it, and this other spin is near. As per our discussion, what is going to happen is the magnetization of the near spin is going to increase, but perhaps ever so slightly, right? The distances can be quite long. The longest distance you can realistically see with Overhauser effect is 5 angstroms if you are really lucky. That is because 1 over r to the 6 is a lot of 1 over r, right? It drops off really rapidly. So 5 angstroms is the realistic maximum. 4.5 is what I would typically guarantee. There are people in the literature who claim 6 or 7 angstroms. I've never believed those particular claims. Okay, but we are going to have slightly enhanced signal there, exactly the same signal here, and nothing, because we've destroyed it there. What people normally do is to get rid of the clutter of all the spins that don't change at all. They just subtract those two spectra. So if we take that, So let's call this A and call that B, and we'll look at, I think it's A minus B. Typically, what we are going to have is this will have a tiny signal. There will be nothing here, and in this case it will be popping steeply down. So in these Overhauser effect experiments, the signal we are saturating is distinguished by pointing down. Then all the nearby spins will have their signals popping ever so slightly up, and all the signals for the spins that are too far to see the target spin, we will not see any signals. So this is a so-called difference nuclear Overhauser effect experiment. In practice, there are various complications to do with the fact that some signals might not perfectly subtract because of sample heating associated with radiation and so on. But there is a class of experiments which are gradient driven using gradient techniques borrowed from MRI, which counter those artifacts. And essentially this is 1970s way, and organic chemists have made great use of it. Books this thick are written on nuclear Overhauser effects and their uses in organic structure determination. So this really became quite famous, and arguably it was this and also the methods that we'll be discussing in the next lecture that contributed to the eventual series of Nobel Prizes for nuclear magnetic resonance. Okay, so this is the first thing I want to discuss, and the last one has to do with the fact that this sigma, if you look at it there, so at these rates, and then at the expressions that I gave for the sigma in your handout, I will not reproduce them because it's going to be just as boring as the previous lecture, but equation 11 in your handout has a sneaky minus. So you can spot the sneaky minus between the two fractions in the brackets. Notice that the self-relaxation rates in equation 10 do not have the sneaky minuses. The self-relaxation rates are always positive because, of course, the spins can only be damped and never enhanced by the environmental noise. But this cross-relaxation rate has a minus, and at a certain viscosity it changes from negative to positive. What that means is that instead of this signal popping up, it will be popping down. So this yellow here is for small molecules. Say in chloroform. And this picture as well. If we have the same spin system but in a protein, the rotational correlation time is much longer. That minus kicks in. Notice that the minus has the frequency sum and the plus has the frequency difference, and instead of popping up, these things will be popping down. So you would have a curve that with roughly the same time scale does exactly the same thing, but it goes through a negative blip rather than a positive blip. So you would have the corresponding curve, and the white curve is for proteins, at least the well-folded ones in water. So the Overhauser effect changes sign at some point as the molecule gets bigger, and unfortunately and naturally that creates a blind spot. So for the molecules of intermediate size, when the rotational correlation time is about half a nanosecond, if memory serves, for protons then the Overhauser effect is 0. And none of this would work, but that's of course easily solved by just picking a solvent of a different viscosity. So if something doesn't work in water, well, if you try it in chloroform, it'll go into the yellow. If you try it in glycerol, it'll go into the white. So you can always shift the rotational diffusion rate by just adjusting the solvent viscosity. And then, well, we fit all those equations of motion and we get distances, and that 20 years ago, or more than 20 years ago, in 1999 was my undergraduate diploma thesis. I was pushing magnetization from protons to carbons using exactly this in a tiny molecule in a non-viscous liquid, and measuring distances and determining the structure in those ways. So that was very laborious because I had to saturate it signal by signal and go through all of this. Better methods have since emerged, but that is the discussion for the next lecture. Okay, summary. I have skipped all of the derivations for those expressions, and take my word for it, you really don't want to see those derivations. And I've concentrated on the physics. The physics is that when you put noise, rotational noise, into dipole-dipole interactions, you switch on 2 extra sets of transitions in spin systems. Previously, you could only flip 1 spin at a time by the pulses, but never 2. Those transitions were forbidden. Now, the flip-flop and the flip-flip become active as well with these rates, which just happen to depend on the inverse 6 power of the distance. And so if we put them to good use, we can measure those distances. What we need to do is find out which observable is straightforwardly dependent on that. Turns out that's longitudinal magnetization, because it doesn't precess, it just sits there and either relaxes or exchanges the magnetization. The longitudinal magnetization is a function of the energy level populations. Energy level populations follow laws broadly similar to chemical kinetics. Depopulation here by dt is just the sum total of what comes in and what comes out. You've seen the first order kinetics, pretty much the same, except instead of concentrations we have deviations from thermodynamic equilibrium, which is just given by the Boltzmann law, Solomon equations. After we apply that, you can see I've also skipped quite a bit of algebra here, right? So we would have had to take this, substitute it 4 times into here, do the simplifications. That's a bit tedious, but after the dust has settled, you get these lovely equations for the evolution of longitudinal magnetization, with 2 types of terms. There's the self-relaxation term that drives it to the thermodynamic equilibrium where it should go by the laws, or second law of thermodynamics really. But there's also this cross-relaxation term which exchanges magnetization perturbations between spins. If we perturb one spin, the other one will know, and it will know in a distance-dependent way. Okay, so why don't we design a pulse sequence around it? Well, firstly, we estimate the amount of magnetization that is going to be pushed, and that's actually quite a lot. So if we fully destroy the magnetization of one spin and keep it destroyed for a while for all of those processes to bite, we can push up to a half of the magnetization of the other spin, and that can be quite a lot if we have a high magnetogyric ratio to the other one. Useful for sensitivity improvement, but we can also turn it into a distance measurement experiment if we just watch all of those magnetizations. We can do a straightforward inversion recovery on L, so invert it, wait for a while, 90 acquire. That's just the straightforward measurement of the T1 time. We've seen that before, but that will give us the self-relaxation rate, rho L. If we do likewise on the spin S, we will get the self-relaxation rate, rho S. And if we watch them both simultaneously and fit, oh well, you cannot do it simultaneously, not on the sort of electronics that was at least available to me in my time, but you can repeat the experiments with different spins being detected. You can get these curves, fit the differential equations just in MATLAB, and get the rates out. The rates are distance dependent. If there are too many unknowns, the experiment is repeated at different magnetic fields, at which point, as soon as we've gathered enough unknowns to extract the distance, we extract the distance and we can tell our diastereomers apart. Laborious, but in a lot of cases less laborious than what chemists would have had to do to tell those diastereomers apart in any other way. All right, any questions? Good. Two-dimensional spectroscopy in the next lecture. where all of this happens automatically all at once and not much labor.